Hello, welcome back to Educator.com and welcome back to physical chemistry. So today we're going to talk about the entropy of the universe and the surroundings. So let's just jump right on in. Let's start with the most fundamental equation that's important to chemists. So you know what, I think I'm going to go to blue today. Okay. So let's start with delta G equals delta H minus T delta S. Okay, now every property in this equation, the delta G, the delta H, the delta S, and the T, in fact, every property that we've been dealing with in all the equations that we've dealt with, they're all properties of the system. So unless we specifically say otherwise, the assumption is that they're always property of the system. Well, not the assumption, they are. They are the properties of the system. Now, so basically this is delta G of the system equals delta H of the system minus T delta S of the system. We don't put it there because that's the general presumption. Now, under conditions of constant temperature and pressure, under conditions of constant temperature and pressure, which accounts for 99.9% of the work that's done in the laboratory, we know that if the delta G is less than 0, then that implies a spontaneous process. That's the very definition of the spontaneous process. The delta G has to be less than 0. That means that the equation as written will move in the forward direction from left to right. Delta G equals 0. This is the delta G of the system. Now, under constant pressure, we also know under constant pressure, well, we know that the delta H happens to equal the heat that's transferred in that process when the process is done under constant pressure. So the heat that flows to the surroundings, the heat that flows to the surroundings is just the negative of the heat that goes to the system. That's it. It's just heat has to come from somewhere. If it goes to the surroundings, it's coming from the system. It's coming from the surroundings, it's going to the system. So the heat that flows to the surroundings is just negative Q. Well, that's equal to negative delta H, right? Because Q is delta H, so negative Q is negative delta H. That's the heat. So this is the delta H of the system. This is the heat that flows to the system. This is the heat that flows to the surroundings. Now, if we suppose a reversible process, so if we suppose a reversible process, well, the ds of the surroundings is equal to minus dq over T minus dq of the surroundings, which is this thing right here, equals minus delta H over T. Well, actually, let me stick with differentials and then I'll do the finite. So minus dH over T. Or we can write it in terms of the finite difference. Delta S of the surroundings is equal to minus Q sub P surroundings. Actually, that's not true. This is just minus, there we go. P over T equals minus the delta H over T. So if I want to know what the change in entropy of the surroundings is, not the change in entropy of the system, I just take the delta H of the system, take the negative sign of it, and divide by the temperature at which this process is taking place. That's all this is. Okay, so now, since we have delta S of the surroundings equals minus delta H over T. We can solve for the delta H. We're just going to move some things around. So we're going to get delta H equals minus T delta S. Okay, so now I'm going to take this delta H equals minus T delta S, and I'm going to put it back in for this delta H. And this is what I get.